If you're serious about World War II infrastructure, survival engineering and, well, the kind of quiet brilliance that kept millions alive underground, then you're in the right place. Before we go any further, make sure you subscribe to this channel and share it with someone who actually cares about real history, because what we're covering today is not surface-level trivia. This is deep, practical knowledge drawn from wartime engineering that still outperforms many modern systems. What most people never realize is that these underground shelters weren't just holes in the ground. They were carefully engineered environments designed to function under bombing, gas attacks, power loss, and mass human occupation for extended periods. The ventilation systems were the difference between survival and suffocation, and many of them are still operational today. Understanding how they worked is valuable not only for historians, but for anyone thinking seriously about long-term underground living or hardened shelter design. Why World War II ventilation engineering still matters more than ever today. World War II forced engineers to solve problems with no room for error. Air had to move without electricity, filters had to stop poison gas, and systems had to keep working even after partial structural damage. These weren't experimental concepts. They were tested daily under combat conditions. What makes them relevant now is that many modern survivalists rely too heavily on powered systems. World War II engineers assumed power would fail, and they built accordingly. That mindset alone is worth studying. How hand-cranked air systems kept shelters alive during total blackouts. One of the most widespread solutions was manual air circulation. In British and German shelters, large hand-cranked blowers moved fresh air through intake shafts and expelled stale air through exhaust vents. These systems didn't just exist as backups, they were primary ventilation in many facilities. In London's deep shelters beneath the London Underground, volunteers were trained to operate these cranks during air raids. From a practical standpoint, this teaches a modern lesson. Mechanical advantage beats electronics when failure is not an option. A properly sized hand blower paired with vertical shafts can ventilate a confined space indefinitely with human power alone. How gas filtration chambers stopped chemical weapons underground. Chemical warfare was a real fear, not a hypothetical one. German shelters, especially those tied to the Maginot Line, used layered filtration rooms filled with activated charcoal, sand and lime. Air was forced through these chambers before entering living areas. These systems still exist today, and some remain functional. The practical takeaway is clear. If you're designing a shelter, filtration must be passive and layered. Relying on a single modern filter is a weakness. World War II systems used redundancy because replacement was impossible during an attack. So let's talk about how vertical intake shafts cleverly use natural airflow to move oxygen. You see, many World War II shelters relied on nothing more than physics. Tall intake shafts were positioned to create pressure differentials between entrances and exhaust points. Warmer air inside the shelter naturally rose and exited, pulling cooler fresh air in behind it. This was actually quite common in Soviet shelters beneath cities like Moscow. No moving parts, no power, no noise, just simple, effective engineering. Even today, for modern application, this principle is still unbeatable. Properly placed vertical shafts with thermal separation can ventilate a space silently and continuously. Now, how did they protect airflow without sealing people in? Well, a major challenge was keeping air flowing while preventing shock waves from entering shelters. Engineers solved this with blast valves that snapped shut under sudden pressure, but reopened immediately after. These were used extensively in German U-boat pens and urban bunkers. This concept is, honestly, critical for modern hardened shelters. Ventilation openings are vulnerabilities unless protected by pressure-sensitive valves. World War II designs show how to balance airflow with protection without complex electronics. And of course, how did they prevent mold and disease underground? Ventilation wasn't just about oxygen, it was about health. Underground humidity causes mold, rot, and respiratory illness. World War II shelters used airflow routing to pass air over cooler stone surfaces, condensing moisture away from living areas. In Japanese island bunkers, this was absolutely essential for long-term occupation. The lesson here is that airflow direction matters as much as volume. Simply moving air is not enough. You must control where moisture settles. So, let's talk about how decentralized vent networks kept shelters alive after damage. One of the smartest designs, honestly, was redundancy. Instead of relying on one large vent, many shelters used dozens of smaller shafts. If one collapsed, well, the others just continued functioning. This approach was really common in resistance tunnels and partisan hideouts across occupied Europe. For modern survivalists, it just goes to show that multiple smaller systems often outperform a single large one, when durability is what really matters. Now, on to how sound-baffled vents kept shelters hidden. Ventilation, you see, creates noise and light leaks. WWII engineers tackled this by using zigzag shafts, baffles, and sound-absorbing chambers. These designs were absolutely critical in resistance networks and command bunkers. The application today is, well, pretty obvious for anyone thinking about concealment. Ventilation does not have to announce your presence if it's designed intelligently. So, let's talk about how overpressure systems kept contaminants out. Some high-value bunkers maintained a slight internal air pressure, which, forced air outward through cracks rather than allowing contaminants in. This approach was especially used in command centers and intelligence facilities. Even without electricity, pressure was maintained through manual blowers and restricted exhaust paths. Interestingly, this principle is still used today in clean rooms and hardened facilities. Now, when it comes to long-term shelters, there's the challenge of balancing airflow with fuel efficiency. In facilities like aircraft factories carved into mountains, ventilation was tied directly to heat management. Exhaust air was routed through machinery spaces to capture warmth before being expelled. Honestly, this integration of systems is something modern survival shelters often overlook. Back in WWII, designs treated ventilation as part of a larger environmental system, not just an isolated feature. Here's something remarkable. Many of these ventilation systems still function nearly 80 years later. The most striking fact is that these systems still work. They were built oversized, simple, and repairable. That sort of longevity is no accident. It's the result of engineering for worst-case scenarios, not for convenience. If you're serious about underground survival, studying these systems is not optional. It's foundational knowledge. If this kind of deep, serious history matters to you, go ahead and subscribe to the channel Share this video with someone who understands why this knowledge still matters, and well, keep digging deeper with us. WWII engineers left us a blueprint for survival. It's up to us to learn from it.